To determine the appropriate transformer size, begin by converting the total amperage to volt-amperes. Multiply the total amperage, which is 250 amps, by the highest voltage, which is 240 volts. This calculation yields 60,000 volt-amperes. Next, divide the volt-amperes by 1000 to convert to kVA. Therefore, 60,000 volt-amperes divided by 1000 equals 60 kVA. A safety margin is generally recommended to account for voltage fluctuations, load variations, and future expansion. A common safety margin is 20 to 25%. To apply a 25% safety margin, multiply the 60 kVA by 1.25. This results in an adjusted kVA requirement of 75 kVA. Therefore, the minimum required transformer kVA rating is 75 kVA. However, to provide sufficient headroom, it is advisable to choose a transformer with a kVA rating of 112.5 kVA or even 150 kVA if available. This is 50% higher than the adjusted requirement. There are several reasons why a 112.5 kVA transformer is a suitable choice. Firstly, the 112.5 kVA transformer will provide a safe and reliable power supply for the heating circuits. Secondly, it will prevent overloading and potential damage to the transformer and equipment. Thirdly, it will allow for future expansion or changes in load requirements without the need to replace the transformer. Using a 100 kVA transformer would be insufficient because it does not meet the minimum kVA requirement of 75 kVA. This could lead to overloading, overheating, and premature transformer failure. Let's delve deeper into transformer calculations and the factors influencing transformer selection. When selecting a transformer, it's not just about meeting the immediate power requirements, it's about anticipating future needs and ensuring reliable operation under varying conditions. Firstly, understanding the load characteristics is crucial. Heating elements typically present a resistive load, which simplifies calculations compared to inductive loads, like motors. However, even resistive loads can exhibit variations due to temperature changes and cycling of the heating elements. Therefore, a safety margin is essential to accommodate these fluctuations. Secondly, consider the ambient temperature and the transformer's operating environment. Transformers generate heat during operation, and their efficiency decreases at higher temperatures. If the transformer is located in a hot environment or a poorly ventilated space, it may be necessary to derate its kVA capacity. Derating involves reducing the transformer's rated kVA to ensure it operates within its safe temperature limits. Thirdly, voltage regulation is an important factor. Voltage regulation refers to the transformer's ability to maintain a stable output voltage under varying load conditions. A transformer with poor voltage regulation may experience significant voltage drops when the load increases, which can affect the performance of the heating elements. Selecting a transformer with adequate kVA capacity helps improve voltage regulation. Fourthly, the type of transformer construction influences its performance and lifespan. Tri-type transformers, which use air for cooling, are commonly used in indoor applications. Liquid-filled transformers, which use oil or other fluids for cooling, are typically used in outdoor or high-power applications. Each type has its own advantages and disadvantages in terms of cost, efficiency, and maintenance requirements. Fifthly, protection devices are essential for safeguarding the transformer and the connected equipment. Overcurrent protection, such as fuses or circuit breakers, protects against excessive current flow due to short circuits or overloads. Overvoltage protection, such as surge arresters, protects against voltage spikes caused by lightning or switching transients. These protection devices help prevent damage to the transformer and ensure the safety of the electrical system. Sixthly, consider the transformer's impedance. Impedance is the opposition to the flow of alternating current and is expressed as a percentage of the transformer's kVA rating. A higher impedance transformer provides better short-circuit protection but may also result in higher voltage drops under load. Selecting the appropriate impedance level involves balancing these factors. Seventhly, energy efficiency is an increasingly important consideration. High-efficiency transformers reduce energy losses and lower operating costs. Look for transformers that meet or exceed industry standards for energy efficiency. Eighthly, the transformer's insulation class determines its ability to withstand high voltages. The insulation class is typically expressed as a voltage rating, such as 600 volts or 5 kilovolts. Selecting a transformer with an appropriate insulation class ensures safe operation and prevents insulation breakdown. Ninthly, consider the transformer's grounding requirements. Proper grounding is essential for safety and to prevent electrical shock hazards. The grounding method depends on the type of electrical system and the applicable codes and standards. Tenthly, future expansion is a key consideration. If there is a possibility of adding more heating circuits or increasing the load in the future, it is advisable to select a transformer with sufficient capacity to accommodate these changes. Oversizing the transformer slightly can save money and avoid the need for a costly transformer replacement later on. 11thly, harmonic distortion can affect transformer performance. Harmonic currents, which are non-sinusoidal currents, can cause overheating and reduce transformer lifespan. If the heating circuits generate significant harmonic currents, it may be necessary to use a harmonic mitigating transformer or install harmonic filters. 12thly, consider the transformer's altitude. At higher altitudes, the air is less dense, which reduces the transformer's cooling capacity. If the transformer is located at a high altitude, it may be necessary to direct its kVA capacity. 13thly, the transformer's enclosure type is important for protecting it from environmental conditions. Enclosures are available in various ratings such as NEMA 1, NEMA 3R, and NEMA 4 to protect against dust, rain, and other hazards. 14thly, consider the transformer's sound level. Transformers can generate noise during operation, which may be a concern in noise-sensitive environments. Low-noise transformers are available for applications where noise reduction is important. 15thly, the transformer size and weight can be important considerations, especially in applications where space is limited. Compact transformers are available for these situations. 16thly, consider the transformer's life expectancy. Transformers are designed to last for many years, but their lifespan can be affected by factors such as operating temperature, load conditions, and maintenance practices. Regular maintenance, such as inspecting and cleaning the transformer, can help extend its lifespan. 17thly, the transformer's cost is an important factor. Transformer costs vary depending on their kVA rating, features, and manufacturer. It's essential to balance cost with performance and reliability when selecting a transformer. 18thly, consider the transformer's compliance with industry standards. Transformers should comply with applicable standards such as those from the National Electrical Manufacturers Association, or NEMA, and the Institute of Electrical and Electronics Engineers, or IEE, to ensure safety and performance. 19thly, consider the availability of spare parts and service. It's important to select a transformer from a manufacturer that provides reliable spare parts and service support. 20thly, consider the transformer's warranty. A good warranty provides assurance of the transformer's quality and protects against defects. In summary, selecting the right transformer involves considering a wide range of factors, from load characteristics and environmental conditions to protection devices and energy efficiency. By carefully evaluating these factors, you can ensure that you select a transformer that meets your specific needs and provides reliable, long-lasting performance. Finally, remember to consult with a qualified electrical engineer to ensure that the transformer selection and installation comply with all applicable codes and standards. This will ensure a safe and reliable electrical system for your heating circuits. When calculating the kVA for a transformer, it is vital to consider the specific application and load characteristics. In the case of heating circuits, the load is primarily resistive, which simplifies the calculations compared to inductive loads like motors. However, it is still crucial to account for factors such as voltage fluctuations, load variations, and future expansion. Firstly, determine the total amperage of the heating circuits. This involves summing the amperage of all individual circuits to obtain the total current draw. In this scenario, there are 15 heating circuits, with 11 operating at 240 volts and drawing a total of 210 amps, and 4 operating at 120 volts and drawing a total of 40 amps. Therefore, the total amperage is 210 amps plus 40 amps, which equals 250 amps. Secondly, convert the total amperage to volt amperes. This is done by multiplying the total amperage by the highest voltage in the system. In this case, the highest voltage is 240 volts. Therefore, 250 amps multiplied by 240 volts equals 60,000 volt amperes. Thirdly, convert the volt amperes to kVA. This is done by dividing the volt amperes by 1000. Therefore, 60,000 volt amperes divided by 1000 equals 60 kVA. Fourthly, apply a safety margin to account for voltage fluctuations, load variations, and future expansion. A common safety margin is 20 to 25%. Applying a 25% safety margin means multiplying the kVA by 1.25. Therefore, 60 kVA multiplied by 1.25 equals 75 kVA. Fifthly, select a transformer with a kVA rating that meets or exceeds the adjusted kVA requirement. In this case, the minimum required transformer kVA rating is 75 kVA. However, it is advisable to choose a transformer with a high kVA rating to provide sufficient headroom and prevent overloading. A 112.5 kVA transformer, which is 50% higher than the adjusted requirement, is a suitable choice. A 150 kVA transformer could also be considered if available. Sixthly, consider the reasons for selecting a 112.5 kVA transformer. Firstly, it will provide a safe and reliable power supply for the heating circuits. Secondly, it will prevent overloading and potential damage to the transformer and equipment. Thirdly, it will allow for future expansion or changes in load requirements without the need to replace the transformer. Seventhly, understand why a 100 kVA transformer isn't sufficient. It does not meet the minimum kVA requirement of 75 kVA and could lead to overloading, overheating, and premature transformer failure. Eighthly, consider other factors that may influence transformer selection, such as ambient temperature, altitude, harmonic distortion, and enclosure type. These factors can affect the transformer's performance and lifespan and should be taken into account when selecting a transformer. Ninthly, ensure that the transformer complies with all applicable codes and standards, such as those from NEMA and IEE. This will ensure safety and performance. Tenthly, consult with a qualified electrical engineer to ensure that the transformer selection and installation are appropriate for the specific application. This will help prevent problems and ensure a safe and reliable electrical system. In summary, calculating the kVA for a transformer involves determining the total amperage of the heating circuits, converting the amperage to volt amperes and kVA, applying a safety margin, and selecting a transformer with a kVA rating that meets or exceeds the adjusted requirement. It is also essential to consider other factors that may influence transformer selection and to consult with a qualified electrical engineer. By following these steps, you can ensure that you select the right transformer for your heating circuits and that it operates safely and reliably. Remember that the calculations provided are based on the information given and may need to be adjusted based on specific circumstances. It is always best to consult with a qualified electrical engineer to ensure that the transformer selection is appropriate for your particular application. Furthermore, always follow all applicable codes and standards when installing and maintaining electrical equipment. This will help prevent accidents and ensure a safe working environment. Also, it is important to periodically inspect and maintain the transformer to ensure that it is operating properly. This includes checking for loose connections, corrosion, and other signs of damage. Regular maintenance can help extend the transformer's lifespan and prevent costly repairs. Finally, remember that electrical work can be dangerous, and it should only be performed by qualified personnel. If you are not qualified to perform electrical work, it is best to hire a licensed electrician to do the job. This will ensure that the work is done safely and correctly. Also, consider the type of load, whether it is continuous or intermittent. A continuous load is one that operates for 3 hours or more at a time, while an intermittent load is one that operates for shorter periods. For continuous loads, it is generally recommended to increase the safety margin to 125% of the calculated kVA. This is because continuous loads generate more heat and can put more stress on the transformer. In addition, consider the transformer's efficiency. Transformers are not 100% efficient, and some energy is lost in the form of heat. The efficiency of a transformer is typically expressed as a percentage. Higher efficiency transformers reduce energy losses and lower operating costs. Look for transformers that meet or exceed industry standards for energy efficiency. Moreover, consider the transformer's impedance. Impedance is the opposition to the flow of alternating current and is expressed as a percentage of the transformer's kVA rating. A higher impedance transformer provides better short-circuit protection, but may also result in higher voltage drops under load. Selecting the appropriate impedance level involves balancing these factors. Furthermore, remember that transformers can generate noise during operation, which may be a concern in noise-sensitive environments. Low-noise transformers are available for applications where noise reduction is important. Also, the transformer's size and weight can be important considerations, especially in applications where space is limited. Compact transformers are available for these situations. Finally, remember to consult with the local utility company to ensure that the transformer is compatible with their electrical system. The utility company may have specific requirements for transformer size, voltage, and other parameters. The local utility may also have additional rules or guidelines that must be followed to ensure compliance with regulations. Failure to do so may result in fines or prevent the system from being activated. By taking these factors into account and consulting with qualified professionals, you can ensure that you select the right transformer for your heating circuits and that it operates safely, reliably, and efficiently. This will help prevent problems, reduce costs, and ensure a comfortable and safe environment